Welcome, and then we, in today's video, we'll be talking about the cross product itself. So we'll provide a definition, and then we will discover why are we learning about the cross product. It would be an invaluable tool to calculate moments in a very efficient way. So let's start with moments, and I want to probably just touch base on what we discussed the other day, right? We have a force in 3D and we have to calculate the moment. So let's just do a brief recap of that. There is a force floating in space, right? Force floating in space with an infinitely long line of action, right? So this dashed line, right? This is my force F, and then this dashed line is the line of action. It's infinitely long. So the question is, what is the moment that this force causes about the origin at point O? Right? So this point is at the origin. So what we have to do is to find the shortest distance between the line of action and that passes through point O, and that we know that shortest distance, it will make a right angle, right? It will be perpendicular to the line of action. Now, depending on the position of F, right, it could be either easy or simple, or it could be really tedious to try to find that shortest distance, right? So the main problem is to find an efficient way to calculate moments. Now, based on this drawing, and just going through the what this drawing appears to be showing us, that line should be something like that, right? Now, in this particular case, it appears to and this distance, right, appears to be hitting that force vector, right in that arrow. But it could be that for some other vectors, right? Let's say for this vector, when we extend the line of action, that shortest distance is actually, right, not touching the force vector, and that is okay, right? It doesn't need to touch the force vector. It just needs to be perpendicular to the line of action, and that it's going to be our distance d. So we can calculate moment equal to force times distance. So this is what we are going to be dealing with, right? And then we'll come back to the physics of the problem, the fact that we want to calculate moments, a bit later on, right? So let's immerse ourselves into the mathematical operation that we will use later to calculate moments, right? So let's keep this in the back burner, and then let's delve into the cross product. So far, right, for vector cross product, so far we have defined two multiplication operations that apply to vectors. For example, scalar multiplication, right? It's just multiplying a scalar times a force vector, right? And then this is simply a scaled vector like this, right? We have also applied the dot product, right, in which we have seen that if we do a dot b, right, allows us to get a multiplication of two vectors, and then the projection of one vector onto the other, right? So this is the second vector operation that has to do with multiplication. And then now we present a third one, right? A third type of multiplication. And it comes with its own set of rules, right? And we call it the cross product, right? We call it the cross product. So we represent it by using this symbol, right? And then we read it as vector A cross vector B equals vector C. In the past, right, if we come back to dot product, in the past we learned that what we obtain from here, right, it's a scalar, right? This is a scalar. The dot product gives us a scalar, whereas the cross product will give us a vector, right? And we will see in a minute why it gives us a vector, right? So, but we read it as vector A cross vector B equals vector C. So how's that work, right? So this vector C, is it parallel to vector A, perpendicular to vector B, right? Parallel to both, perpendicular to both. What is the orientation of that vector? How big is it? right? How big is it? Is it small? Is it big? Is it equal to A, equal to B, equal to the multiplication of A or B, right? So let's go to that, right? So A cross B gives us a vector, right? C is a vector, right? Such as in this case, the magnitude of C. The magnitude of C is given by, right? The magnitude of C is given by the magnitude of A times the magnitude of B times the sine of theta, right? The sine of the angle that these two vectors make, right? So if we have vector A over here, right? Vector A over here and vector B over here. So this is the angle that the tails of the two vectors make. So the sine of that vector times the magnitude of one times the magnitude of the other will give you the magnitude of the vector. How's that C vector look like, right? To find the direction of C, right, we use what we call the right-hand rule, right, in which the index finger, right, right, will represent the orientation of A. The middle finger will set it up in the direction of B. And then if we do that, right, index on A, right, vector A, middle finger on vector B, the thumb will give us vector C. And we can see that vector C is perpendicular to both A and B, right? Perpendicular to both. So right-hand rule, index finger on vector A, middle finger on vector B, and the thumb will give you vector C, right? A cross B equal to C in the direction of your thumb. So just to summarize these rules, right? So we have them written here. Index finger in direction of A, right, will be the first vector. Middle finger in direction of B is the second vector, and that gives you the thumb, which is pointing up 90 degrees. That will be in the direction of C. Now, take a look, right? Will it be the same, right? Would it be the same? Can we obtain C, right? Can we obtain C as B cross A, right? Can we obtain C equal to B if we cross V with A? So to do that, apply the right-hand rule, right? And then try this at home, but don't break your hand, right? Don't break your hand. This is the B vector over here, and this is the A vector over here. Now put your index finger on B, right? And then try to put the middle finger on A. You will discover that you have to turn your full hand, right? And then hopefully you will be finding that now the thumb is pointing down, right? So the cross product is not commutative. The order matters, right? The order matters. So this is not right? This is not the same, right? So B cross A cannot give you C. So let's just put a big cross over here, right? That it cannot give you C. So the order is important, right? The order is important. So let's investigate a little bit what are some of the nice things and interesting things about the cross product. So if we remember the definition, right? If we remember the definition, let's just set a vector A over here, right? Vector A over here with magnitude A, right? Magnitude A. And let's set up another vector B over here, right? And let the magnitude be B, right? The absolute value of B, right? That's the magnitude of B. Right? This is the angle theta between the two, right? And then just by applying simple trigonometry, right? Just by applying simple trigonometry, right? This distance over here, that is going to be the magnitude of B sine of theta, right? That is the magnitude of B sine of theta. If we make use of the parallelogram rule, right? If we make use of the parallelogram rule and we define a parallelepiped, right? Parallelepiped here, right? It's kind of a rectangular shape, right? The area of this shape, right? The area of this blue shape will be base times the height. Well, the base is this one, and the height of that shape is this one over here. So the area of the blue shape is equal to the magnitude of A times the magnitude of B times the sine of theta. Well, this just happens to be the magnitude of the cross product between A and B, right? So this is the magnitude of this, right, is equal to the magnitude of the vector that you get when you cross these two vectors. So the magnitude of the cross product of A and B, right, is equal, right, graphically, to the area of this rectangular shape, right, that you make with vectors A and B, right? So some other interesting things about this, right? Just to summarize, I have vector A and vector B, right? This is vector, right? This is vector C, right? A cross B, right? Put your index finger on A. Put your index finger on A, right? Put your middle finger in B, and you will see that vector C actually shoots up as it shoots upward, right? And it makes right angles, right? Makes right angles with both vectors B and A. And its magnitude, of course, right? Its magnitude is just magnitude of A times magnitude of B times the sine of theta, right? That these two vectors make with each other. So this is the graphical representation of the cross product. Still, right? Still, no clue that this will allow us to get the moment caused by a vector with respect to a point, but hidden, right, in the past few slides, that is exactly, right. I already gave you a very strong hint, right? But well, even in this slide, it's here, right? It's hidden. I won't tell you where. Oh no, I'll tell you where it is, right? It's on the definition, right? It's on this scalar definition of the cross product. How we will use it to calculate moments, right? But don't tell anybody, right? Let's assume that we haven't spoken of that just yet, right? So another interesting thing, right? What happens if we have parallel vectors, right? Well, parallel vectors. What is the cross product between these two? In order to understand this, right, it's probably better if we use the scalar definition, right? And then for that we have to use the magnitude of one vector times the magnitude of the other times the sine of the angle that they make. So what angle do they make, right? Parallel vectors, what angle do they make? Well, we can argue that well, they make an infinite angle, or they don't even cross, right? But we agree, right, or the convention is to agree that they make a 0-degree angle, right? If we superimpose one vector onto the other, you will see that parallel vectors actually they make a 0-degree angle with themselves. And then we apply the definition, right? Sine of 0, right? This is sine of 0 degrees is equal to 0. And then we find that the magnitude of the cross product of the two, right, vector C, is 0. So in fact there cannot be any cross product, or we can say that it's equal to 0. So when two vectors are parallel, that, right, the cross product is equal to 0, and it comes from this definition. So in the same way that we try with our index finger and middle finger, and I hope you didn't break your fingers at home, right? We saw that the commutative law is not valid, so we cannot say that A cross B, right, is the same as B cross A, right? We found that it is the negative, right? We saw that the thumb points the other way, so we can say that A cross B is equal to negative B cross A, right? B cross A. What happens if we multiply times A scalar, right? What happens if we multiply times A scalar? So if we multiply times a scalar, right, we find that a scalar A times A cross B, right? We just it's the same as multiplying the first vector or multiplying the second, right, and multiplying everything at the end, right? It'll make no difference. We can use distributive law, right, in which we can actually cross if we have vectors V and D added together, and then we cross with A, right? We can actually cross A cross B first, and then add that A cross D. So distributed law works fine with vectors. What happens if we have our vectors in CVN? And to understand the cross product of vectors that are given to us in CVN, which will be quite common, right? It's important, or it's interesting to see what happens when we do the cross product between unit vectors. For example, we have our old friends, right? I hat, J hat, and K hat. And then I am going to ask you to do the right hand rule, right? For these ones, don't break your hands at home, right? Let's see what happens, right? Let's see what happens. So these are all the possible cross products we can do with our unit vectors, right? So let's see if we can figure out all of them. So I cross J, right? So this one over here, I cross J. So looking at this figure over here, right? Index finger in I, and I'm going to do it with you here in the video. You cannot see me, but I'm doing it. So index finger in I, right? Middle finger in J, and you can see that your thumb is actually pointing towards the K hat axis. So this is correct. So we just verify this one. Let's pick another one. Let's pick careful, right? Careful. I don't want you to hurt yourself at home. So let's pick this one. What about this one? K times J, right? K times J. So index finger in K, middle finger in J, right? And you see how your thumb points, right, on the other side of I hat, right? So that's why they are saying that it is equal to minus I hat. So in the same way, we can do another one. Let's actually do the or take a look at what happens when we do the cross product on one vector upon itself, right? I hat cross I hat, well, these vectors are parallel, right? They make 0 degrees, so we get 0 as the cross product. So do we have to memorize this, right? What if we cannot do the right hand rule with our fingers, right? Well, there are memory aids that we can actually use. For example, right? For example, this over here, right? This tool works like this. If we start, let's say, I hat, right, cross J hat, right? This little circle here says that we are going to have positive values if we go counterclockwise, right, clockwise. So I hat cross J hat, right, gives us positive K hat. So I hat positive, J hat positive gives us positive K hat. And if we do the other way, right, if we do it the other way, we are going to have, right, according to this sense over here, we have negative results. So let's do, for example, let's do, let me choose blue color to do the other one. So what about we do J hat cross I hat. So in order to do this, we have to go this way, J hat cross I hat, right? And then we obtain minus K hat. So let's find it here. So J hat, let me find it. J hat, I'm trying to find J hat cross I hat. Well, the only one that I see is I hat, strange, right? Well, is this one, right? Is this one again? Is this one again? But we saw that if we invert, right? We invert or we change the vectors or the order, we are going to have the negative of the vector. So it's fine, right? And it follows the rule. So it's kind of tedious, right? But if we use the right hand rule with our fingers, right, will be fine. Or we just use tools such as this one, right, that we saw here. Let me just use the eraser so you can take a look, right? You can also use these rules to help you figure out what is the sense of your vectors, right? So in the general case, right, you're going to have your vectors A, right? Let me just use red color. So your vectors A and B, right? Your vectors A and B. In CVN, right, given in CVN format, such as this one. And then you may be interested in calculating the cross product. So let's actually do it, right? If we remember the distributive law works, so actually, if we apply the distributive law, right, so one vector cross the other, right, and it's just a matter of getting all these products, right, and we see that we start getting, for example, the first product is the component A in X cross the component V in X, and then this is well, these two are scalars, so scalar times scalar, and then we have I hat cross I hat, so we have all this product here. So I hat cross A hat, do you remember what is equal I hat, well, parallel vectors? Well, you may remember that all these products in which we have the same vector, right, because these guys are parallel, right, we can actually cancel them, right, because they are equal to 0. And then your cross product is equal to this very nice formula. So let's take a look, right? So some of these terms are positive, 3 are positive, 3 negative, right? There is no clear indication, right? So this is the component of A in Y times the component of B in Z minus the component of A in Z times the component of V in Y times I hat, right? And then we can do the same for the second term over here, and then for the other term over there. You see that the subscripts change, right? And it may be troublesome try to remember the formula, right? Of course, if you believe you can remember the formula, you will save a lot of time, but actually we have a tool that will allow us to get the formula quite nicely, right? And then we are going to make use of this of the tool called determinants. So you may remember that you saw determinants probably in high school when you were solving systems of equations, right? We'll use them here as an aid to actually calculate the determinant, right? Determinant. So instead of the previous equation that had many terms, right? 6 of them actually, we write these vectors like this, right? So first, in the first row, I had j hat and k hat. Then the first vector, order is important, remember? Order is important. The components, the CVN components of the first vector. And then in the third row, we put the CVN components of the second vector. And then we proceed to treat this as a determinant. If you remember, determinants follow specific rules in order to evaluate them. Let's try it with numbers. So I have two vectors, right? T1 equal to 4i hat minus 3j hat plus 5k hat, right? And vector T2 equal to 4 times I hat plus 6 times j hat minus 2 times k hat, right? And we want to find vector T1 cross vector T2, right? So we write them over here. First row, I hat, j hat, k hat components. Second row, right, just the magnitudes of I hat, j hat, k hat of the first vector. So 4 minus 3 and 5, right? 4 minus 3 and 5. And then 4, 6, and minus 2. 4, 6, and minus 2. And then we proceed to solve the determinant. So watch out for the formula, right? This is just a mechanical, kind of a mechanical procedure. So these are set rules on how to do it. So we start by repeating the first two rows, and then you see that I have repeated I hat, j hat, k hat, and 4 minus 3 and 5. Then I write these diagonals, right, crisscrossing the products, and take a look, right? Take a look. I'm starting at the very top, and I finish at the end, right? And I cross these three quantities, right? Important not to left anyone behind, right? And I have to multiply the numbers that lie on the diagonals, right? Now, the left-hand side, right? The left-hand side, I'm going to multiply by an additional minus 1. And in the right-hand side, I'm going to multiply times a positive 1. So let's remember. So let's try this, right? Let's multiply the numbers in the diagonals. Important. Numbers in the left-hand side, right, will get an extra minus 1 to be multiplied with. So let's do it, right? So in the first diagonal, right, this diagonal in the left, I have 4 times minus 3 times k hat times minus 1, right? In this second diagonal over here, I have 6 times 5 times minus 1 times I hat. Third diagonal, I have 4 times j hat times minus 2 times minus 1. And then what about in the other side? So let's use blue color over here. So this is minus 2 times minus 3 times I hat times plus 1. I don't even write it. This diagonal over here will be equal to 4 times 6 times k hat times plus 1, right? And then the last one is equal to 4 times 5 times j hat times plus 1. And then we simplify the products and we obtain these components, right? Right hand side, left hand side. I have to add them together. I have to add the I hat components, add the j hat components, and add the k hat components. So adding the products, we obtain this vector, and this, my friends, this is equal to T1 cross T2, and we obtain a vector, right? What we were expecting. So determinants, right? Some of your instructors they like to use a few other techniques, right? It's still a determinant, but it's another technique to obtain the determinant value, right? It's called cofactors, and I recommend you try it out, right? If your instructor likes to use cofactors or any other, there are other ways to calculate the try those techniques, right? You may or may not like this way of doing determinants with the diagonals here. I just personally like it, but your instructors may prefer another technique. So make sure you take a look at what they use, and then we are just evaluating the determinant. Now, if you don't want to learn one way or the other, right, all we have to do is to memorize the formula with the 6 terms that we saw before, and then there is no problem. So next up, we are going to actually relate moments caused by forces to cross product, right? So not hidden, right? But in some of these slides, we have already given the key on how cross products, right, can be used to evaluate the moment, right? The moment that a force causes about a point. So see you on the other side, in which we will actually talk about this, right? Moment of force about a point, and we will use cross product to do it. Well, thank you. See you on the other side.